we know that this programmable interval timer, it is used for performing the timing and the counting operations for the microprocessor. So it is used to, we can write here that it is used to perform the timing and counting operations. And also it can be used to interrupt the microprocessor at certain time intervals. So this programmable interval timer, this IC, it has three timers in it: timer 0, timer 1 and timer 2. And these timers, they can be loaded with a count, and the timers are going to decrement the count until its values reaches to 0. So it has the three timers: timer 0, timer 1 and timer 2, TM0, TM1 and TM2. Now these timers, or we can say counters, they are loaded with a count, and this count is then decremented. Now this is decremented until its value reaches to 0. So when the count it is equal to 0, then the programmable interval timer, it generates a pulse. Okay, and this pulse can be used to interrupt the microprocessor, or it can be used to perform various types of operations. Like it can be used to generate the pulse, it can be used to interrupt the microprocessor, it can be used to count the number of events. So various types of operations, they can be performed which involves the timing and counting. So they can be performed using this method. Okay, now these timers of the programmable interval timer, they are programmable, and they can be independently programmed to work in different types of modes. So we can say that each timer can be programmed independently. So each timer, it can be programmed to work in different types of modes. So this 8253 IC, it has 6 different modes. These modes are modes 0, 1, 2, 3 till 5. So we have the modes: mode 0, mode 1, mode 2, mode 3. So these are the 6 different modes of the programmable interval timer IC 8253. Now which mode it is operating with, that means the 3 timers, in which mode they are operating, that is decided by the control word of the 8253. So let us first study about the control word of the programmable interval timer. So this control word of the 8253, it is an 8-bit word having the 8 bits D7 to D0. D7, it is the most significant bit, and D0, it is the least significant bit. Now these bits, they are described as follows. The D7 bit and D6 bit, these bits are used to select the counters and the timers, the three counters like counter 1, counter 0 and counter 2. So these are the selection bits for the counter. So when these two bits, they are 0 0, then counter 0 will select it. If these bits are 0 1, then counter 1 is selected. If it is 1 0, then counter second is selected. And when it is 1 1, then these bits are illegal. It will not work in any of the modes. So these D7 and D6, they are the select counter bits. Then we have RL1 and RL0. These two bits, they are deciding that which mode, or we can say that which operation will be performed by the timer. Okay, so their values, they can take different combinations like 0 0, 0 1, 1 0 and 1 1. So when its value is 0 0, then the counter latching operation is performed. When it is 0 1, then so these two bits, they are deciding that which operation is to be performed by the timers. When it is 0 0, then the counter latching operation is performed, means the output of the counter will be latched for the next clock period. Okay, next clock cycle. Then if its value is 0 1, then read and load the LSB only. That is the least significant bit only you have to load in the timer, because timers, they are the 16-bit down counters. So 16-bit data will be loaded into the timers, and 16-bit data will have the most significant bytes and least significant bytes also. 88 bits will be there. So when it is 0 1, then the least significant bits will be loaded into the timer, and when it is 1 0, then the most significant bits will be loaded into the timer. Loaded also means they are written into the timer, and read means the count value of the timer will be read by the microprocessor. So these two operations are the read and write operations with the three counters. Then we have 1 1. This is the read and load LSB, then MSB. Means this function 1 1, it is used to load or write or read the 16-bit count. Okay, so here we are having the 88 bits count only, and here we are having the 16-bit count. So first the lower order bits of the count will be loaded, and then the most significant bytes of the count will be loaded, or it will be read. So they are, we can say that these are related with the reading and loading the data into the counters. Then comes the M2, M1 and M0 bits. These bits are the mode selection bits. Mode selection bits means these bits are going to decide that in which mode the timer which is selected by the D7 and D6 bit, it will work. So there are 6 modes, mode 0 to mode 5. So the mode selection bits, their value will be if it is 0 0 0, then mode 0 will work. If it is 0 0 1, then mode 1. If it is x10 means it can have 0 value also and it can have 1 also. So it can have two combinations like 010 and 110. So when these two values are there, then the timers will work in mode 2. Then we have x11. X11 means it can have any of the values 0 or 1. So the combination will be either 011 or 111. So when both these combinations, if any of these combination is there, then the timers will work in mode 3. Then we have 100, then mode 4. And when we have 101, then mode 5. So these 3 bits, they are deciding that in which mode the timers are going to operate. Okay. So here we have the mode selection bits. Then this is the BCD counter. Okay, because the counters, they can be used to count binary data also and BCD count. Both type of counts can be loaded into the counters. So here this BCD, this bit D0, it is going to decide that the count which is loaded into the counter, it is either a binary count or a BCD count. So when the value of this bit, it is 0, that means it's a binary counter. And if its value is 1, it means that it is a BCD counter. So both types of counters can be counted by the timers. So we can have, if it is 0, then it's a binary count, and if it is 1, then it's a BCD count. So this is the control word of the programmable interval timer 8253 and 8254. You can see that how the 8 bits of this control word, they are deciding that which counter is to be selected, then what operation it has to perform, and in which mode the timer has to work, and the type of count which is loaded into the counter. So all this information, it is contained in this control word. Now on the basis of the data which is there in the control word, the mode will be decided and the timer which is selected, that will be decided. So now let us come to the different modes of the 8253 IC. As I have said that this 8253, it can operate in 6 different modes, and these modes are decided by the bits M2, M1 and M0. So let us start with the mode 0, and let us first see that what these modes are named as. So there are 6 different modes. So mode 0, it is known as the interrupt on terminal count mode. Mode 1, it is known as the programmable one-shot mode. Mode 2, it is the rate generator mode. Mode 3 is the square wave generator. Mode 4, it is the software triggered mode. And mode 5th, it is the hardware triggered mode. So these are the 6 different modes of the 8253 or 8254. First we will start with mode 0. So this mode is selected when in the control word we have the 3 bits M2, M1 and M0 as 000. Now, what is the work of the timer in this mode? What the timer is going to do? As the name suggests that this mode is known as the interrupt on terminal count. So when the count will be initialized, then at every clock pulse, it will be decremented till its value becomes 0, and the value of the count when it is 0, that is called the terminal count, and when the terminal count is reached, the timer it is going to produce an interrupt pulse. A pulse will be generated that is going to interrupt the microprocessor. So this mode it is used to generate an interrupt for the microprocessor. So I have said that this mode it is used to generate an interrupt. Now you have to load the count into the microprocessor into the interval timer. So this in this mode, first the count will be loaded and then it will be decremented by 1 at each clock pulse. So in this mode, the counter will start counting from the initial count value which is loaded into it. Okay, so the count value will be loaded into the counter which is selected by the control word. In the control word, we have the SC0 and SC1 select counter bits which are going to select the counter 0, 1, 2 and 3. These counters will be selected and then the counting will start from the initial count value and it will be decremented to 0. Now the counting rate of the counter, it is equal to the input clock frequency. That is the rate at which the clock pulse is generated. At the same rate the counting will be done. Means at every clock pulse the count value it will be decremented by 1. Now for every counter, we have the out, gate and the clock inputs. Out is the output of the counter and clock and gate are the input. So let us see that what will be the status of these signals when the counting is going on. So when the control word is written in the control register, then the control word will decide that which counter is selected and it will be working in which mode. So in mode 0, the select counter bits, suppose like counter 1 is selected, so those bits will be 0 and 1. And then the count value, it is also loaded into the control word, and also the mode, it is also decided by the control word. So when this control word is written and mode 0 is selected, then the out pin, it is set low. Okay. So the counting or the decrementing the counter means decrementing it by 1. It will start one clock cycle after the count is programmed. So it means that when the count is loaded, then after one clock cycle, the counting or the decrementation of the counter is initiated. Okay. So it will start after one clock cycle. So the output signal of the counter, it will remain low until the counter reaches 0 value. Now this out value, it is low until the counter it reaches 0. Means at every step, like if we have initialized the counter by 4, then at every clock pulse it is decrementing like 4, 3, 2, 1, 0. So when this counter is decrementing the count value, then the out signal, it remains low. And when it has reached 0, 0 has been achieved, like terminal count has been achieved, then the out will become high, and it will be high until the counter is either reloaded or the new control word is written in the control register. So when the counting is done, then at that time the out signal, it is low, otherwise it is high. Now, what about the gate signal of the counter? The gate signal, it will remain active high for normal counting. When the counting has been done by the counter, then at that time the gate signal should be high. If it becomes low at that time when the counting has been done, then the count value, it is latched, and when it again becomes high, then the counting is again automatically, it is done in the same manner. Okay. So we can write here that when the gate signal, so if the gate signal, it goes low, then the counting get terminated, means it is stopped, and the current value of the count, it is latched till gate pulse goes high again. So to understand the operation of mode 0, let's take an example and let's see that what will be the timing diagram of the counter in it. Now the first figure in this, it is showing the mode 0, in which the first signal, it is the clock pulse. So you can see that this is the clock input to the counter. Now this is the right signal, because the right signal, it is loading the count value into the counter, and also the control word, it is written in the control register. So when this right signal is low, then the count value will be loaded into the counter. Now here the count value is 4. So this fourth count value, it is written or loaded into the counter, And initially you can see that the gate signal here, it is written that the gate signal is high. So when the gate signal is high and the counter value or count value is loaded into the counter, then at after one clock pulse the counting will start. Means the counter, it is going to decrement the count value. So this is after one clock pulse the counting has been started, and at every clock pulse the count value is, it is decremented by 1. So initially it was the count value was 4 was loaded into the counter. So after one clock pulse it becomes 3, after one clock pulse it becomes 2, till its value comes to 0. And 0, it is the terminal count, means the counter value has become 0. Then the, you can see that when the count value it has achieved 0, initially the out signal was low, and when the terminal count has been reached the out signal goes high. Okay, so here in the description I have written here that the counting starts one clock pulse after the count is programmed. So you can see that the counting has been started after one clock pulse. Out remains low until the counter reaches 0. So you can see here that when the terminal count has been reached, the count, this out signal, it has become high. So out will be set high until the counter is reloaded or the new control word is written. So now the out signal will be right, it will be high until here a new control word or a new counter has been loaded whose value is 2. So here the count value was 4 and here new counter has been loaded which is 2. Okay. So the out signal will be high until the counter is reloaded or the new control word is written. Now next we have about the gate signal. The gate signal remain active high for normal counting. So for normal counting here it is written that the gate signal is high for this. Okay, you can see that after one clock cycle the counting has started, and again the out signal it goes low when counting has been done by the counter. So 2 is loaded, so 2, then after one clock pulse it is 1, after one clock pulse it is 0. So when again the terminal count has been reached, the out signal it has become high. So when counting it is going on, then out is low, and when counting is not going on, then it is high. And gate pulse, it is always high. It should have to be high for normal counting. Now there is another example in this where again the count value 4 is loaded into the counter, and after one clock pulse the counting has started. So the gate signal it was initially high, so when it is high the counting has to go on in its normal way. But here the counter, this gate signal it has become low. So when the gate signal goes low, the current count value which is 4, it is latched until the gate signal again goes high. So when the gate signal is low, you can see that the current count value was 4. So 4 has been latched by the counter until the gate signal it has become high again. Now again the gate signal is high. So for every one clock cycle, the counter will be decremented by 1 until its value becomes 0. So here we have 4, 3, 2, 1 and then 0. And when the terminal count has been reached, the out signal becomes high. So this timing diagram, it is showing the status of the right signal, clock pulse and out and gate pulse, that how in mode 0 the status of these signal it is changing when the counting has been done by the counter. So this was mode 0 and this was the timing diagram for it. Now let's come to mode 1. Now this mode it is known as the programmable one-shot mode, and this mode will be selected when 001 is loaded in the control word bits. So in this mode, the 8253 programmable interval timer, it can be used as a monostable multi-vibrator, and the gate signal, it is used as the trigger input. So in this mode, the gate signal, it is used as the trigger input, and the out signal, it will be initially high, and out will go low on the clock pulse following a trigger to begin the one shot pulse. If we take an example, or if we see the timing diagram for it, this is for mode 1, and here it is the clock pulse, then we have the right signal, then gate signal and out signal. So through the right signal, the counter value, it is loaded into the counter, which is 4. So here the count value is 4. So in this, the out signal, it will be initially high, and the out will go low on the clock pulse following a trigger to begin the one shot pulse. If we take the example here, so in this we have the mode 1 here, and in mode 1, the this is the clock signal, then right, gate and the out signal. Right signal, it is writing the control word or loading the counter with the count value. So here the count value is 4. Now you can see that this gate signal, it is initially low. So when the it is, because in this mode the gate signal, it is acting as the trigger input. So when the gate signal is high, then only the counting will begin. So here you can see that when the gate pulse has become high, so after one clock cycle, the counting has initiated. Okay, so the counting is going to start after one clock pulse when this gate signal is triggered. So here this gate signal has been triggered because it has changed from low to high. So counting has started. Every time the count value will be decremented till its value becomes 0 or terminal count has been reached. And when this counting is going on, then this out signal is low. And when terminal count has been reached, the out signal again becomes high. So here I have written that out will be initially high, out will go low on the clock pulse following a trigger, means following the trigger, then the out pulse will go low. After one clock pulse, the out will go low, and to begin the one shot pulse. So the out signal, it will remain low until the counter reaches 0, and out will then go high and remain high until the clock pulse after the next trigger has reached. Okay, so here you can see that when this trigger has been given, then after one clock pulse, counting has started and out signal has become low. And when terminal count has reached, then this out will go high, and it will be high until the next trigger has been given to the through this gate signal. Okay, and when the next trigger will be given, then after one clock cycle, again the out signal will go low. So in this way, the out signal, it is responding to the counter which is loaded into the count value which is loaded into the counter. Now, after writing the control word and the initial count, the counter is armed. Okay, so here when this control word has been written or the count has been loaded into the counter goes into the armed condition. Okay, so now when in this armed condition, if again a trigger is being given to the counter, means again the gate input is going to trigger the counter, then the counter will be again loaded and again the counting will start. Okay, so this triggering, if we give another trigger in this armed condition, then the counter will be reloaded and the out signal will be low on the next clock pulse and again the counting will start. And this triggering, it results in the starting the one shot pulse. So here we have given, if when this first trigger is given, then counting has started, but in between if another trigger is given by the gate signal, then again the counter is reloaded and again counting has started, and this will generate one pulse which is known as the one shot pulse. Okay, so this starts the one shot pulse. That is why this mode is known as programmable one shot mode. Now the initial count value of n, because here the initial count value in our example it was 4. So this initial count value, it will result in n clock cycles. In that n clock pulses will have one shot pulse, n pulses in that. Okay, so an initial count of n will result in one shot pulse, n clock cycles in duration. So an initial count of n will result in one shot pulse, which are n clock cycles in the duration. So this was the mode 1, which is known as the programmable one shot mode. The next mode we have is the mode 2, which is known as the rate generator, and this mode will be activated when 0 x10 will be loaded into the control word. X means it can either be 0 or it can either be 1. So 010 and 110 both will initiate mode 2 in the counters. So this mode, in this mode, the device acts as a divide by n counter, and this mode, it is used to generate a real-time clock interrupt. Now let's see that what will be the status of the out and clock gate and the write signals in it. So in this mode, like the mode 0 and mode 1, counting is going to start the next clock cycle after the count is loaded into the counter. So in this mode, the out signal, it will remain high until the counter value reaches 1. Means when the count value is loaded into the counter, suppose 4 is loaded, then after every clock pulse, it is going to be decremented by 1 until its value reaches 1. Okay, and then the out signal, it will go low for 1 clock pulse, and then after 1 clock pulse it will then go high again, and the whole process repeats itself. Let's take see the timing diagram for the mode 2. This mode 2 is known as the rate generator mode. So here we have the clock pulse, then write and out signal. You can see here that the clock count 4 is loaded into this counter. So here count value is 4, and the gate signal, it is initially high. So when the gate signal is high, then after 1 clock pulse, the counting is going to start. Means after 1 clock pulse, its value will be 3, then 2, then 1. Now you can see that it's not going to 0. That means terminal count is not reached in this mode. In mode 0 and mode 1, the counter is decremented until its value is becoming 0. But here the counting is going on until its value has reached to 1. Now when 1 is reached, then the out signal, it will go low for 1 clock cycle, and again the count value will be loaded into the counter, means 4 will be loaded, and again the counting is going to start. So here the counting is 4, 3, 2, 1. Then again it will go low for 1 clock cycle. Now the new count value which was loaded is 2. So now the counter has become 2, and then 2, 1. When it has reached 1, then again it will go low for 1 clock cycle, and then again 2 will be loaded. So in this way, the out signal will be generated in the mode 2, and you can see that every time the process is repeating itself until and unless the counter is reloaded. Okay, so here 4 was there, so 4 will be decremented until its value has become 1, and when it is 1, then 1 for 1 clock pulse the out signal will go low. Then this 2 will be loaded, so 2, 1, again it will go low for 1 clock pulse. So here I have written that out will remain high until the counter reaches 1, and it will go low for 1 clock pulse. Out will then go high again, and the whole process repeats itself. So the time between the high pulses, it depends on the preset count in the counter's register. Preset count means the count which was earlier loaded into the counter. So you can see that the out signal, it is high, then it is low, then again it is high, then low. So it is becoming low when the counter is has reached 1. Okay, so this time between the high pulses which we are getting at the out signal, it depends on the preset count in the counter register, means what count value you have loaded into the counter. So 4 was loaded, so for 3 clock cycles the out signal was high. Then if 2 is loaded, then for only 1 clock cycle it is high. So this for the time when this out signal is high, it depends it depends on the preset count in the counter register, and this value, this time, it is calculated by the formula. The value to be loaded into the counter equals to the input frequency and the output frequency. Means for what time period we want the out signal to be high and to be low. So for this F input and F output, we can calculate the value which is to be loaded into the counter. So in this way, the signal is generated, or we can calculate the rate of the signal. One important note you have to take in mind for this mode 2, that values in the count register, they ranges from n to 1. N is the count value which is loaded into the counter, and it is decremented until its value reaches 1. So this thing you have to keep in mind, that the register in the mode 2, it never reaches 0 value. So the terminal count, it is never achieved in the mode 2. So we have seen the timing diagram also for the mode 2. So now let's come to the mode 3. Mode 3, it is known as the square wave rate generator. So let's see the features of this mode 3. So this mode 3, it is similar to mode 2. However, the duration of the high and the low clock pulses of the output, they will be different from mode 2. So in mode 2, the clock pulses will be high for the number of times the count is loaded, and it will be low for it was low for one clock pulse. But in the square wave generator, the duration of the high and the low clock pulses, it is different. Otherwise, it is similar to the mode 2. So in this mode 3, the number of times the output, it is high and low, it is decided by the value of the count. Okay, so if n, it is the number which is loaded in the counter, or it is the count value, then if this count value is even, then output will be high for n by 2 counts, and output will be low for n by 2 counts. So for equal number of times, the output will be high and low. So let's take an example. If we are taken that the count value, it is 4, then the output will be high for 2 clock cycles, it will be high, and for 2 clock cycles it will be low. Now if this count value, it is an odd number, then output will be high for n plus 1 by 2 counts. So if we take an example that n is equals to 5, then n plus 1 by 2 means for 3 clock cycles the output will be high, and for 2 clock cycles the output will be low. because output will be low for n minus 1 by 2. So 5 minus 1 by 2 will be 2. So if this count value it is an odd number, then for 3 clock cycles it is high, and for 2 clock cycles it is low. And if it is even, then for n by 2 and n by 2 clock cycles, the output will be high and low. So let's see the timing diagram for this mode 3. So this is the timing diagram for mode 3, here first figure. So this diagram, we have the clock pulses, then we have the write signal which is used to write or load the counter with the count value and to write the control word in the control register. So here we have taken the count value as 4 and 5. So when the count value is 4, then the output will be high for 2 clock cycles and low for 2 clock cycles. So initially the gate signal was high, you can see here. So when the gate signal is high, then output signal is initially high. Then after 1 clock cycles the counting will start. So 4, then divide by n means minus 2 you have to do here. So 4, 2, then again the counter is reloaded, it is 4. Then it will be low for 2 clock cycles, again high for 2 clock cycles, again low for 2 clock cycles. Now here the counter it is reloaded, 3 has been given. So for 3 we have, it is an odd number, so 3 plus 1 by 2 clock pulses it will be high, and for 3 minus 1 by 2 clock pulses it will be low. So here we have high for 2 clock pulses and low for 1 clock pulse. Okay, so in this way the counter it works in the mode 3. Now if we have here, the gate signal was initially high, it has to be high for normal counting process of the counter. Now when it is low, here the counter is low, so you can see that the count value was, initial count value at that time was 2. So that count value will be left, and again the counter will be reloaded and counting will continue in the same fashion. So here we have 5, so for 3 clock pulses the output will be high, for 1 clock pulse it will be low. So it is starting from 5. So we have here, you can see for 2 clock pulse it has to be low, but here the gate signal is low, so it is not going here, and again when the gate is becoming high, then counter is reloaded, and for 3 clock pulses it is high, for 2 clock pulses it is low. So for 3 it is high, 2 it is low, here it is 3, 4 it is high, and here we having 1 because the gate signal has become low. In this you can see for 2 clock pulses it is high, for 2 clock pulses it is low. Again for 2 clock pulses it is high, for 2 clock pulses it is low. Then new counter has been reloaded here. So for 3 we have 2 clock pulses for it is high, and 1 clock pulses it is low. So this is in this way it will be a square wave generator, because here you can see that a square wave is generated for 2 clock pulses, means a square wave is there when the counter value it is an even number. Okay, so this was mode 3 square wave generator. Now let's come to the mode 4. This mode will be activated when in the control register the mode bits, mode selection bits, they are loaded with 100. So let's see the features of this mode. So in this mode 4, after the control word and count is loaded, the output will remain high until the counter reaches 0. So initially the output is low, and when the control word and count is loaded, the output will be high, and when it has reached 0, then it will become low. So you can see that in the mode 4th, the counter is loaded. Here the count value is 4. So gate signal is high for the normal counting, and out signal it is initially high. So when this count value, it will be high until the counter has reached to 0. And when it has reached to 0, it will go low for 1 clock pulse, and it will again become high. So the counter will then generate a low clock pulse for 1 clock cycle, which is also known as a strobe. And after that, the output will become again high. So initially the output was high. It will remain high until the counter reaches 0. And when it has reached 0, it will generate a low clock pulse for 1 clock cycle. And after that, it will again become high. So output is always high, but it will become low for 1 clock cycle only when this counter value has reached to 0. So whenever we want to generate one strobe, we can use this mode 4, which is known as a software triggered strobe. Software triggered strobe we are saying here because through software, through some programs and instructions, we are generating this. And software, because the mode is selected through writing the control word in the control register, so we are using the software instructions for it. So it is called software triggered, because this 1 clock cycle, which is also known as a strobe, this clock pulse can be used to trigger some device, okay, as a triggering input for some device. So that is why it is known as software triggered strobe. Okay, now you can see here this gate signal has to be high for normal counting process of the counter. Now when this gate signal, if it becomes low, then this count value, it is latched till the gate signal again becomes high. So when this gate signal, it is again high, then again the counting process will be resumed, like 4, this 4 was the this 4 count value was latched. So from 4 it will be 3, 2, 1, 0, and then it has become 0, so it will be low for 1 clock pulse output, and again it will become high. So you can see that the gate signal for normal counting process, it has to be high. If it is becoming low, then the count value, it is latched until the gate signal becomes again high. Okay, so this was mode 4, which is the software triggered strobe. Now let's come to the mode 5, which is the hardware triggered strobe. This mode is similar to the mode 4, but here the triggering, it is done through some hardware circuitry. That is why it is known as a hardware triggered strobe. So the operation of mode 5 is based on this, that the counting process, it is triggered by the gate signal. Now in mode 4, the triggering, it was through this low, it was low for one clock pulse, and the triggering is just done through the software instructions, like writing the control word in the control register, we can trigger this mode. But in mode 5th, here the triggering, it is done by the gate signal. So gate signal, it is used to trigger the counting process, and after receiving the control word and the count value, the output will be set high. So you can see in the timing diagram here that this is the timing diagram for mode 5, showing the status of all the signals. Here we have the clock signal, then the gate signal, and in this mode 5, the gate signal is used as the triggering input. So when the control word and count is loaded into the counter, here we are using the count value 4. So when 4 is loaded into the counter and this gate signal is high, then counting starts till the counter value reaches to 0. And when this is 0, the output will go low for one clock pulse and again it will become high. So it is similar to this mode 4, that when the counter has reached 0 value, then the output will be low for one clock pulse. But here the triggering, it is provided by the gate signal, but in mode 4, the gate signal is always high. Okay, and here triggering was provided by the software instructions. Now come to the value when this gate signal, it is high, so the counting, it is done 4, 3, and then 2, 1. Now again it is becoming low, the gate signal has become low, and again it is triggered, it is providing, it is changing from low to high. So again this count value will be loaded and the count processes repeat. Okay, now after this clock pulse, because after 1 the count has to be decremented to 0, but here again the triggering is provided by the gate signal. So 0 has been not achieved here in this count value, and this low clock pulse is not generated here. So when the counter has reached the value of 0, then only this low clock pulse will be generated. Otherwise, in between, if the triggering is again provided, then the counter will be again reloaded and it will be decremented till its value becomes 0. And when it is 0, one low clock pulse will be generated. So here you can see that the difference between mode 4 and mode 5 is that here triggering is provided through software instructions, and in mode 5 the triggering is provided by the hardware circuitry, that is the gate signal. That is why it is known as the hardware triggered strobe. So here I have written that after receiving the control word and count, the output will be set high. Then once the device detects the rising edge on the gate input, it will start counting. You can see here rising edge means the value of the gate signal, it is changing from low to high. That will be the rising edge. So once the device detects the rising edge, it will start counting. So it will start decrementing the count value. And when the counter reaches 0, the output will go low for one clock cycle, and after that it again become high. So these are the 6 modes of the programmable interval timer 8253, the mode 0 to mode 5th, and we have seen the timing diagrams also of all these 6 modes, so that you can easily understand the working of these 6 modes. Now come to the operations which are performed by the programmable interval timer 8253. We have seen the control word of 8253, that the 7 bits of the control word from D0 to D7. So the 8 bits of the control word, they define different functions. The bit D7 and D6, they are used to select the bits. They are used to select the counters, counter 0, counter 1. and counter 2. Then comes the bit number D5 and D4, and these bits, they define the operation which is performed by the counter. So the various types of operations performed by the counter, let's come to it, that there are three operations. First is a simple read operation. Then comes the counter latch command. And then we have read back command. So these are the possible methods, three possible methods of reading the count value or reading the counters. Okay, so when these operations were performed, we have like reading or writing the counters and then loading the counters also there. So one of the operation was the how we can read the count value from the counters. So the count value, it can be readed by three methods: the simple read operation, then counter latch command, and then read back command. So let us first study the simple read operation. So in the simple read operation, the count value which is there in the counter, it will be simply read by the microprocessor. So in this, the counter is selected with the A1 and A0 input lines, and then the clock input of the selector counter, it is initiated through either the gate signal or any other circuitry. Now when we want to read the count value, then we can use the mode in which the count value we want to read, and this is done because this clock input of the selected counter, it is initiated by using either the gate input or the external circuitry. Because if the count value, it is decremented, suppose the count value is 4, then 3, 2, 1, and then 0. So when it is decremented and at that time it is read, then the microprocessor, it is going to read the value 3. But if in between the count value read count value is read, then it will give an undefined result. So that is why the clock input of the selected counter, it is initiated by either the gate input or any other circuitry here. So this was simply the reading operation of the count value. Then comes the second is the counter latch command. So this counter latch command, the SC0 and SC1 bits of the control word, they are used to select one of the three counters, and then the bits D5 and D4, these bits distinguish this command from a control word. Now if a counter is latched, means the count value it is latched of the counter, then sometime later it is latched again before the counter is read. So if we see that, again take an example of the count value 4, so the counter will decrement it like this: 4 3 2 1 and 0. Now if the count value is latched at 3, means it is 4 3 and then it is latched, so its value is again 3, and again the gate input is given, so 3 2 1 and then 0. So if a counter is latched and then sometime again later it is latched again before the count is read, the second counter latch command is ignored. Okay, so this is 4 then 3, then it is latched, and again suppose at 2 it is latched again. So if this latched value 3 it is not read by the microprocessor, then this second latch command it is ignored. Okay, so once the microprocessor or this timer it is latching the output of the counter, then the microprocessor has to read this latched value, otherwise the second latch command it will be ignored and the counter will not be latched again. Okay. So if the count value is read by the microprocessor and second time it is latched, and if the microprocessor is reading the count value, then the count read will be the count at the time the first latch command was issued. So after that, if it is reading the count value suppose at 1, so the latched value will be the value when the counter is latched when this first latching command was issued. That means the latch value will be 3, not 2. When the second latch command was given, it was ignored and only this 3 value will be read by the microprocessor. So this is the counter latch command. Next is the read back command. So this read back control command, it is used by the timer when it is necessary for the contents of more than one counter to be read at a same time. So when the programmable interval timer or when the microprocessor it wants to read the contents of more than one counter at the same time, then this read back control command is used. Now the read back control command, we have the control word for it for this command. So let's see it. So the control word for this readback command is that D7 and D6, they are always put at 1 and 1, and A0 and A1 lines, they are 1 1. So here we have D7 and D6 as 1 1 for the readback control command. Then D5 bit, it is the count, which is saying that if it is 0, because count and bar is there, so it's an active low signal, so it will be active when its value is 0. So when this D5 bit is 0, then the count value of the selected counter will be latched, and the selected counter, it will be decided by the 3 bits D3, D2 and D1. Then if this D4 bit, it is 0, so it is assigned for the status signal, which is also an active low signal. So here if this bit is 0, then the status of the selected counter will be latched. Count is 0, then count will be latched, and if the status is 0, then status of the selected counter will be latched. Then these are for the counter selection. Then D3 is 1, then counter 2 is selected. If D2 is 1, then counter 1 is selected. If D1 is 1, then counter 0 is selected. Then this D0 bit, it is always kept at 0, and it is reserved for future expansions, for future modifications in the IC. So the chip select signal, it is at 0, so this 8253 is selected. A0 and A1, it is at 1 1, so that this control word can be loaded into it. And then read signal, it is 1, because the count value has been read, because this is the read back control command. So the read signal is 1 and write signal is 0. Okay, because this control word, when we want to load this control word into the control register, then write has to be 0 and read signal is 0 when we want to read the counters. So once when this control word, we want to write it in the control register, then this write signal has to be 0 here. So these are the three operations, the three methods by which the status and the count value of the counters, the counter 0, counter 1 and counter 2, they can be read by the microprocessor. Now let's come to the, because we have studied the control register, control word, the operational modes we have also studied, and then we have studied the methods of reading the counter. So now we are left with the status register of the 8253. So let's see the control word of the status register. The status register shows the status of the out pin of the counters. Every counter, it is having one output line and two input lines. So two input lines were the clock and the gate, and one output line is the out pin. So the status of the out pin, it is indicated by the status register. So this status register, it shows the state of the output pin, and it can check the counter, it is in null state or not, and it is also used to see that how the counter is programmed. So let's see the control word for this status register. So this is the control word for the control for this status register. These are the 8 bits for it. D7 bit is for the output pin. So this D7 bit, if it is 1, it means that the out pin of the selected counter, it is 1. And if it is 0, it means that the out pin is 0. So this is status register, it is showing the state of the output pin. Now come that to check that the counter it is in null state or not, then we have this D6 bit for the null count. So when this D6 bit it is 1, it means that the counter it is in null state, and when it is 0, it means count is available for reading. Null state means that the counter has reached to a value of 0. So when the 0 value it is reached, then this bit is set, and when the count value it is available for reading, then this bit is reset, it means it is 0. Then we have RW1 and RW now. These are the counter programmed mode, and M2, M1, M0. These are also for deciding the modes. RW1 and RW0, they decide the operations like read operation, write operation, or to read or write the lower bit first and then MSB first. So this is just like the control word which we have studied earlier. Then BCD, it is to decide that whether the count which is loaded, it is either a BCD count or a binary count. So this was the control word for the status register. So in this video, we studied about the operational modes of the programmable interval timer 8253 or 8254 IC. We have seen that there were 6 modes of operation from mode 0 to mode 5, and we have also studied the timing diagram of these modes. Whenever you want to read these modes, then first we read the theory and then relate it with the timing diagram so that you can easily understand the operations of these modes. So I hope that this topic is clear to you. Thank you.